So what tables are used for a PowerOpI logistics solution? That's the subject of this series playlist. Please like the videos and subscribe to the channel. This sequel has been shown as an example for a PowerOpI logistics project, but other solutions will have some pretty close analogies. The sequel gives some context on how the tables to be described in this video are used together. The physics of tables described in this video apply to any PowerOpI solution. Tables used in a PowerOpI solution are usually contained in Excel workbooks as Excel structured tables. Within Excel, they can execute in-table calculations using index, match, SUMIF, structured keys, and so forth to prepare raw data within themselves to participate in joins by database environments. For the joins, they can be used by Power Query, and, using the VBA linking code described in video PowerOpI Structure Part 4 in this channel, they can be used with MS Access or SQL Server. Alternatively, they could be tables native to one of those database environments, or they could be Excel worksheets or named ranges. But most of the time, Excel structured tables. Most of the structured tables are manually constructed and managed. Calculated fields replicate as records are added, so only raw data fields need to be entered or copied in once a table is set up. There are probably several of these structured tables in a workbook, but tables for a solution don't need to all be in the same workbook. Each table linkage into Access, SQL Server, or Power Query requires a fully qualified address, so tables could be distributed among multiple workbooks and databases. In fact, these workbooks and databases could be distributed among different computers, which leads to scenarios for distributed use. For example, tables could be managed by development, by supply chain, by operations. It also implies that table locations might change over time, and since table linkages require fully qualified addresses, relinking would be required. There will be a video on this channel covering relinking and providing some automation for that. A tactical note on PowerOpI source tables used with databases. For MS Access or Power Query, the tables can live in workbooks also containing pivot reports driven from database queries linked to the tables in those same workbooks. However, pivot reports driven from SQL Server queries must not be contained in a workbook also containing source tables for those queries. This will be covered in the video to be supplied on this channel, covering use of SQL Server in a PowerOpI solution. In the SQL example on this slide, in-table calculations and field imports are assumed to have been done in Excel prior to execution of this query using index, match, and SUMIF with structured keys. Then in the query, extended quantity and cost aggregation of a single level of bomb explosion are calculated. The query aggregates fields and aggregates records from the join tables. The table linkage into the database is not shown in this query, but the video on PowerOpI structure on this channel describes MS Access link tables, and the video on SQL Server describes use of both linked servers and Open Rosette. This video focuses on identifying characteristics of the set of tables used in a PowerOpI logistics solution as an extensible example. Other videos on this channel will cover details of tables handling dates and of product structure using a BOM, bill of materials, or product tree. The first table we'll cover contains basic information about each element type, both build and buy, used in the project. Buy elements are purchased as being in a completed state, perhaps in a specified configuration. Intrinsic characteristics of these items are listed in table elements for use in calculations in other tables. Buy items include components such as ASICs, power supplies, cables, and switches. These items in most cases are used to build a higher level item. Components might be used in building a circuit board, power supplies, or off-the-shelf cards to build a chassis. Remember, I'm using a logistics solution as an example. The PowerOpI methodology isn't tied to that, so you can look for analogies in your situation. Build items are those whose BOM and builds are managed by you through a development lifecycle process. Logistically relevant spec characteristics of these items are listed in table elements for use in calculation in other tables. If your project involves developing an assembly, in earlier stages of development, this assembly would be a build item using component buy items and build steps to build the assembly, perhaps at a CM. Later in the product, when you're testing the assembly as built by a manufacturing partner, you would consider the as-built assembly as a buy item bought from the CM. So both the buyable components of the assembly and an as-built configuration of the assembly would be in your table elements. The must-have fields in the table identify the item by fields element name, description, supplier, and VPN for vendor part number, and identify its anticipated production cost in field production cost. An item ID key allows linkage from other tables. There could be other keys provided for local use to calculate values of fields in this table, but they'd be data-specific and are not addressed here. There are separate videos in this channel on table BOM construction and on table dates construction, and both describe structured keys for local calculations. Best practice fields further characterize the item. Lead time is purchase lead time. Item class is a high-level description of an element such as a server or processor chip. Useful life or cap life, along with production cost, are criteria for capitalizing the element. Rack space, MTBF, thermal, power, and weight are intrinsic properties of the element. Connector distinguishes one or more connectors, for example, network or power connector needed. Slots describes the number of available slots in an assembly. More characteristics could be provided, such as Ethernet slots, describing how many of the available slots are to be configured for network. Material special handling might indicate values for single source or prototype or consigned to CM, and so forth. Web links might be provided for supplier datasheet, distributor ordering, and so forth. Calculated fields in table elements. Fields cap life and account rule are used with production cost to calculate field account spec used in table BOM or table dates with element rev in those tables to determine capital or expense accounting. An item ID structured key is provided to be used from foreign tables to retrieve data about each listed item. Item ID key value is based on field element name of the line item. Table alloc is a table that describes assignment of elements to be used in the project. Must-have fields include field element for identification and build rev for revision, org and owner identifying responsibility for use of the element, sysid being a system name identifying the next higher level element if there is one, incorporating the allocated element, quantity used, test use, and config with obvious meanings, and purchase request number PR by which this element is acquired when that becomes available. For chip development, SKU corner, lot, wafer, and die to be used can be specified, as well as assembly config noting packaged configuration. Grid to normalization is added functionality. Ideally, table allocation is a table in normalized form. That may be impractical if distributed users are to input their own information, for which a grid organized table may be more practical. A separate video in this channel will describe normalization, including tools for conversion from a human usable grid organized table to a normalized table friendlier for joins and pivots. Calculated fields in table alloc include alloc ID key based on field element and alloc rev key based on fields alloc ID key and rev. Next table is table BOM. Table BOM recursively describes the build structure of all project elements across multiple revisions. Table BOM is used for explosion of the build structure from allocations in table alloc to assemblies and components to be built or bought. A separate video on table BOM in this channel gives a broader description of table BOM. Fields in table BOM identify element and element rev, subassembly, subassembly rev, and subquantity identifying a comprising subassembly and its quantity needed for a single element. An element can be comprised of several subassemblies, each specified in its own record in table BOM. An element with no subassembly, such as a buy item, simply lists itself as a subassembly with subquantity equals 1. Sub-build by, a value retrieved from table elements, indicates build by status for the subassembly on that line. An in-table rollup calculation of subcost, subassembly cost, multiplied by subquantity results in X cost, meaning extended cost. Subcost rollup was shown as an example in the video OPI Structure Part 2 Table Calcs in this channel, and is covered also in the video on this channel on Table BOM. Other characteristics from table elements could aggregate in assemblies and can be similarly rolled up, including rack space, weight, thermal, and power. Some other fields from table elements can be useful in calculations, including lead time, useful life, MTBF, or slots. Some might be used for characterizing an element in reports, slots, rack space, or connector. Field account spec is retrieved from table elements and used in field CapEx for field rev to resolve capital or expense accounting. This is described in the table dates video on this channel, but could just as well be calculated in table BOM. Structured keys in table BOM are BOM item key, used to fetch data from table elements, BOM item key in, used to join table alloc into table BOM, and BOM item key out, used to join subassemblies into table BOM for recursive explosion and to join subassemblies into table dates. Calculated fields in table BOM include BOM item key based on subassembly name, BOM item key in based on element and element rev, BOM item key out based on subassembly name and subassembly rev, sub build by retrieved from table elements based on BOM item key, sub cost, local item count, and X cost are shown as an example in OPI Structure Part 2 table calcs. X cost is based on sub cost and sub quantity. Local item count is based on elements, element rev, and subassembly, and creates a key used to determine the sub quantity of items dependent on the quantity of the sub-element named. Table dates contains dates for project elements, typically for build, buy, integrate, test, and distribution milestones. Table dates is based on the MPP exported table brought into Excel as table task table access import. The name is an example. You would choose one for your project. Table dates is a table normalized on element name, build rev, and scheduled task for start date and finish date. A separate video in this channel will cover details of calculations in table dates. Must-have fields identify element name, build rev, and task. Start date and finish date specify dates retrieved from imported table task table access import. Keys provided are schedule item rev key and schedule item rev task key. Unscheduled element handling adds functionality and needs some additional fields. A Gantt plan basically has to cover built elements and integrations. Buy elements such as cables, power supplies, switches, or racks can be purchased, which is a common and simpler process. There are lots of buy elements, so it's a pain to include them all in a Gantt to determine dates for them. So items can be assigned to use dates for a scheduled item in the Gantt to be ready for a build or integration step that uses the scheduled item to which it's aliased. These are called unscheduled items, and in table dates they can be aliased to build items to use those dates. So we can add rows to table dates for all unscheduled elements. Fields are added to table dates to specify the aliased element. These are fields called useItem, useRev, and useMilestone, and specify the scheduled element, rev, and task alias to by this unscheduled element. Also, key fields normally based on element name and rev are changed to refer to the alias to element. So when the unscheduled element is referenced, dates for the alias to useItem, useRev, and useTask are returned. Purchasing fields also add functionality to table dates. Many of the unscheduled items are buy items, so purchase milestones must be added that are not present for built scheduled items. Rows are added, particularly to unscheduled elements, for tasks called material purchase date to place a PO, considering lead time, and pay date for invoice due date. Field lead time retrieved from table elements for the unscheduled element modifies field start date for an alias material purchase task. Field build loc is manual entry to specify where the build or buy is to be accomplished. Further functionality fields. Gantt dates from imported MPP plan table task table access import are calendar dates, but any financial reports in PowerOpI will need to be translated to fiscal year and fiscal quarter. Fields FY start and FQ start translate to field start date and to fiscal year and fiscal quarter. If needed, similar translations could be added for finish date too, but so far I haven't seen need for this. Field account spec is pulled from table elements and used in-field CapEx with field rev to resolve CapEx accounting. This is described in the table dates video on this channel, but could just as well be calculated in table BOM. So, calculated fields in table dates. Schedule item rev key is based on use item and use rev. Schedule item rev task key is based on schedule item rev key and use milestone. Lead time and account spec are retrieved from table elements based on element. Use item, use rev, use milestone are set to element rev and task if the item is scheduled, or are overridden by manual entry to indicate the alias element for an unscheduled item. Start date and finish date retrieve dates for use item, use rev, and use milestone from imported table task table access import. Start date subtracts lead time if the task in that record is material purchase. CapEx takes the value of account spec, except if account spec value is var. Then it takes value exp for early values of field rev that would be expensed, or cap for later rev values that can be capitalized. Fields FY and FQ are based on start date and finish date as shown in the video on this channel for table updates. Table builds is a transformation of table dates to grid organization showing multiple date fields for each element and rev. One pivot table report we'll want to build is a build plan representation for operations, which is a table with each row by element and rev of task dates for key ops and supply chain steps, and showing build location and aggregating quantity to be built. Data throughout the tables in this video is almost certainly normalized. There's a video on this channel about normalizing data for best use in joins and pivots. However, date information is unique in that it's dates from steps in the Gantt, and dates can't be aggregated as values like quantity and cost can be. So normalized date information is difficult to use to build a table of dates. It's likely that we'll want to denormalize multiple date records describing multiple Gantt steps for an element rev to use those Gantt dates in a pivot as row labels where we're aggregating element quantity and cost. Therefore, table builds more or less duplicates table dates with task dates denormalized, that is, in grid format. Table builds is usually hand-built, pulling dates from either table dates or from the same MPP import, table task table access import, from OPI task data part 3 export. Table builds includes fields for element name and build rev, and alias specifications use item, use rev, and use milestone. A field is provided for each task date, likely including material purchase, fab out, SMT, assembly, test, integrate, and add engineering. Also included are fields lead time, pay date, FY, FQ, and build loc. A build rev key, structured key, provides access to each element rev record from a foreign table. So calculated fields in table builds. The table retrieves dates from table task table access import into columns, each naming a task. Each retrieval is based on the name of the table builds field in which it resides, such as material purchase, fab out, etc., to identify the task. Each column specifying the task date must also specify whether the start date or finish date is to be retrieved for the task date. Lead time is retrieved from table elements based on element. FY and FQ are derived from date field pay date, with indices set to specify your fiscal year, as described in the video on this channel for table dates. Field loc is manual entry to specify where the build is to be accomplished. Build rev key is used to join this table to aggregate fields from this table and is based on element and rev. Table perch is for tracking material as it's acquired and distributed. Material acquisition has a life cycle all its own, something like RFQ placed, quote received, PO submitted, PO approved, PO placed, ETA, item on hold, item delivered, latest status date, latest status, item location, and item disposition. There are several black holes in this sequence into which your project can disappear while some remote bureaucracy considers your request, requiring frequent and regular status checks so you know when and where to kick butt. An item order will not all be received simultaneously or distributed simultaneously, so location and disposition of the physical parts must be tracked as well. Data to track in table perch will likely include item name, item rev, quantity ordered, quote ID, PO number, ship tracking number, then a date field for each purchase lifecycle step listed. Calculated fields in table perch include item rev key, based on item ID and item rev, and field latest status date, which is the date of the latest update among the purchase lifecycle steps, indicating current state in the POPR lifecycle. Table test result is for building ASICs, where wafer test data plays an important part in completing a build, using specified bins for packaged ASICs built for use in circuit boards and using assemblies. A basic test data table structure is shown. Data available is likely determined from fab supplier test data. The structured key is likely a structured key containing lot ID, SKU corner, and test bin. Item rev key would be based on element and rev, where element names the die functionality and rev specifies the fab build. In-table link dependencies suggest a specific order of table creation shown in the colored table from top to bottom. You can build table skeletons in your project workbook containing the fields described in this video, even if table data isn't available yet, and then populate the tables over time as data becomes available. Building and updating the tables in the order of the dependencies shown allows you to build calculated fields, naming fields from the dependency tables. If the dependency table and fields aren't there, you can't build those expressions. The order shown for building these tables is also convenient when updating them with new or updated project data. Then, as you enter project data in each table, values will fill into calculated fields and you can visually verify correctness. Not mandatory, but it's helpful to ensure correctness as the data is entered. Notice that you need to have at least skeleton setup of the MS project files in order to set up table dates and table builds. This order will be correct, whether a single query with multiple joins as the SQL example shows, or building multiple single join queries dependent on each other in a stacked order. Both the colored table figure and the query structure on this slide show join participants in order, including join keys to use from each table. This concludes the OPI table design summary. More video sequences on this channel will cover handling of dates, BOM table structure, data normalization for joins and pivots, use with SQL Server, system development considerations, schedule optimization, and OPI deployment configurations. You can find more information on the website. Please subscribe to this channel and like the videos.